Alrighty, so we're going to begin Chapter 5, which covers the skeletal system. Just a quick overview of the skeletal system. There's about 206 bones. They all have cartilage in between the joints. Joints are technically called articulations, so get used to hearing them called that. Overall functions of our skeleton include support and protection. Those are the big ones. It's also helping with movement, helps with mineral homeostasis, maintaining certain minerals in our body. There's also blood cells that are produced within our skeletal system, as well as fats that are stored, triglyceride storage. So some specifics here. It provides a framework for our soft tissues and points of attachment for muscles. It also provides a hard barrier to protect some internal organs. Think about our brain and where our heart is, both protected by hard bones. Serves as levers for those force-producing muscles, and they help to produce the movement along with the muscles. They also provide mineral homeostasis, blood cell production, as well as triglyceride storage, as I mentioned. We'll get into those details when we get into some specifics later on. So the long bones and short bones are two different types of bones in our body. The long bones are longer than their width, and they tend to have a slight curve with them rather than being straight. They can have circular or kind of knobby-like ends. These are the bones that make up our arms and legs, fingers and toes, whereas short bones have an equal length and width, so they're more cube-shaped. These would be like our ankle and wrist bones. There's also flat bones, like the bones of our skull and our sternum, as well as our ribs would be classified as flat bones. They're thin. They provide muscle attachment for muscle attachment surfaces. And then there's irregular bones, like the bones of our face and the bones of our vertebral column, which have very complex shapes that don't fit into the other categories. So long bones, these are the kind of quintessential bone that we use to study bone structure. They have a diaphysis. The diaphysis is the middle of the long bone, so it's the shaft, so to speak, of the long bone. It's actually hollow. In adults, that's where some fat is stored. It has yellow marrow inside of it, which is fat or triglyceride storage. The ends of the long bones are called the epiphysis. These are solid structures. In the adults, this is where the red bone marrow is. That's where red blood cells are produced. The ends, the outside edges of these ends, are covered by articular cartilage, which is a special type of hyaline cartilage. The epiphyses of neighboring bones come together to form those movable articulations. The entire bone is covered by a little blanket called a periosteum that's made of connective tissue covering the entire bone. Here you can see what I mean. This periosteum peels off. If you've ever ate chicken right down to the bone, you might notice that periosteum is that outer kind of clearish or opaque-ish covering to the bone. If you were to crack open the long shaft of the bone, the diaphysis, you would see that it's hollow. This would be where lots of fat is stored. Some people like to eat that yellow marrow out of their chicken bones, for example. You also have the epiphyses. These are the ends of the bones. There are two epiphyses to these long bones. The distal epiphysis would be the one that's further away, and the proximal epiphysis would be the one that's closer to the body. This bone that we're looking at here is a humerus. That's your upper arm bone. So the head of this upper arm bone would be the proximal epiphysis. This is what fits in at your shoulder joint. This distal epiphysis is what forms the articulation at your elbow joint. Here you can see the articular cartilage covering the ends of this bone and the ends of the bone up here. And you can see that this inside of the epiphysis is made of a spongier material called spongy bone. That is where lots of red bone marrow is stored, and that's where your red blood cells are made. So if we look at the microscopic structure of bone, if we look at bone under a microscope, it has a very distinctive look to it. It's actually a type of connective tissue, you may recall from Chapter 4. It's also known as osseous tissue. It has a matrix to it, just like all of our connective tissues do. Mostly water, a little bit of collagen fibers as well, and there's lots of crystallized mineral salts. Mostly calcium, but there's some magnesium and other salt deposits in there as well. Those are deposited by special cells called osteoblasts. Osteoblasts are bone building cells. Blast building. Composed of compact as well as spongy bone. Spongy bone has that spongier appearance. Compact bone is a more dense type of bone. Calcification is the overall process of depositing those mineral salts. That calcium and other minerals get laid down by those osteoblasts, as I mentioned. The hardness of a bone is determined by the degree of calcification. That's also going to provide some flexibility as well as tensile strength within the bones. You want them to be very strong and very sturdy, but you also want bones to give and flex a little bit. So it's a nice balance between the two properties. And that's brought to you by the collagen fibers, which have that flexibility yet sturdiness to them. So there's a couple different types of cells that we would find in microscopic bone. You have those osteoblasts, as I mentioned, those are the bone builders. Eventually they become entrapped in the matrix, and then they're termed osteocytes, so they kind of build a little calcium nest around themselves and are then called osteocytes. Osteoclasts do the opposite of osteoblasts. Osteoblasts are builders. Osteoclasts are digesters. They're going to reabsorb the minerals and reabsorb the proteins that are within the bone and release those proteins into the blood. So if you're not bringing in enough calcium, for example, into your body, these osteoclasts are going to begin to break your bones down and take the minerals out of your bones so that your body can use the calcium for its homeostasis. Osteocytes are those mature bone cells that were once osteoblasts. They help to regulate bone homeostasis. And osteogenic cells are a special type of stem cell that can divide and become an osteoblast. If your bones are going through a period of non-growth and then all of a sudden they start growing again, these osteogenic cells, which are sometimes called osteoprogenitor cells, they're going to form osteoblasts, and then the osteoblasts can continue to help your bone to grow. Here you can see what I mean by distinctive look. If you check out this actual picture of a osteon or bone cells, you see that it kind of looks like a tree trunk. You have that center area, which is called the central canal, and that central canal is surrounded by lots of concentric lamella. Concentric lamella are basically the rings that make up this structure. You see these little dark patches. Those are the individual osteocytes within our bone cell. If you look at the cartoon version, you can see what I mean a little better. The central canal has that nutrient artery and nutrient vein running through it, those blood vessels. The blood vessels are then going to branch into smaller canaliculi, is what they're called, little canals. And those little canals are going to serve as connections between the osteocytes. They're connected to each other, so nutrients can be exchanged from osteocyte to osteocyte, all coming out from those central blood vessels. This hardened matrix, this kind of tan material, that's that water, that's the collagen, those are the minerals, those are all of the things that are laid down by the osteoblasts. So as those osteoblasts are building bone, they're literally adding another ring to the circle of the osteon. The osteon is this entire circle structure itself. It's made of osteocytes connected by canaliculi, all coming out from that central canal of blood vessels. So compact bone provides protection and support. It also helps to resist any stresses produced by weight and movement. This is found just deep up to the periosteum, and it composes the bulk of the long bones. So when we're talking about long bones, the majority of our long bones are made of compact bone. Our femur, right, our humerus, all of the large long bones of our body, mostly made of compact bone. The ends of these bones have spongy bone within them, but the majority of the bone is made of compact bone. So let's talk more specifically about some of those structures I was just identifying for you. The osteon itself is that cylindrical or circle-shaped unit of compact bone. That's the tree trunk looking structure that I showed you. The lacuna are the special little spaces where the osteocytes live. They're connected by the canaliculi. The canaliculi are little canals that allow those osteocytes to connect to each other and exchange nutrients and waste products. The lamella are the concentric tree trunk layers that extend out from that central canal. And the central canal, or Haversian canal, that's the very center of our osteon that contains the blood vessels, the lymph vessels, to help provide nutrients and get rid of waste for the entire osteon structure. That was compact bone. Spongy bone, or cancellous bone, has a slightly different structure. This is the bone that's found in the short, flat bones, as well as the diaphysis, the inner diaphysis and epiphysis of our long bones. So just the very inner part of our long bones and the ends of our long bones is where you will find this spongy bone. Spongy bone contains trabeculae. Trabeculae is kind of like stalactites and stalagmites of a cave. They're these irregular lattices that form this kind of sponge-like network inside of the bone. It's covered by compact bone or cartilage, and in between the trabeculae is where you'll find the red bone marrow, which produces the red blood cells. This animation here goes through bone formation for you. Let's talk about bone formation. Bone formation occurs in 4 stages. There's the initial phase during the embryonic development. There's bone growth that occurs during infancy, childhood, and adolescence, so as you're growing in size. Then, once the bones stop growing, they're constantly undergoing this process of remodeling. Remodeling would be kind of like taking a little off of this side and putting it on that side of the bone. And that's all in response to pressure and use. If you're not using your bones, if you're not exercising, if those muscles aren't pulling on the bones, then those bones are not going to grow and maintain their strength. Bone formation is also going to occur if broken bones occur. If there's fractures, it will allow for those bones to regrow. Let's start with the embryonic form in a process called intramembranous ossification. This is when bone forms directly from an embryonic connective tissue. So you can imagine this embryo, which is basically just full of certain types of cells. Well, some of those cells, called mesenchyme, will develop into bone. And this is pretty much what happens. This is not intramembranous ossification that we're looking at here. This is endochondrial ossification. This is different. Instead of, let me just flip back for a second. Instead of the bone forming directly from the embryonic connective tissue, in this case, the bone is forming from cartilage. So you can see cartilage has been laid down. In this case, hyaline cartilage has been laid down. You can see the diaphysis, the epiphyses. Well, there's some chondroblasts, which are special cartilage-producing cells. They start growing and differentiating into the bone cells. Those chondrocytes are going to begin to differentiate and start laying down calcified matrix. That calcification is going to basically spread throughout the cell, and as that happens, special osteogenic cells, those stem cells, are going to differentiate into the osteoblasts, and the osteoblasts are going to lay down more bone matrix and then become osteocytes, and then more osteocytes will grow, so on and so forth, until you get a fully formed bone. And you can see the progression of it here. The development of that inner medullary cavity is continuing to happen. The ends of the bones, the epiphyses at this point, are still uncalcified matrix, still cartilage, but as the diaphysis continues to grow, the ossification centers continue to kind of pop up along the ends of our bones, ossifying that uncalcified material, and eventually the diaphyses and epiphyses are both calcified and full of functional osteons. This animation goes through the dynamics of bone and the dynamics of bone tissue. Let's talk about how long bones grow. So there's actually cartilage within the epiphyseal plates. that's going to cause them to lengthen through the process of chondrocyte division. Let me show you what I mean. Pull up my little whiteboard here, break out a cruddy drawing, but hopefully it will help you. So if we look at a long bone here, again, very bad drawing with this touchpad mouse that I'm using. But there's our long bone. Here's an epiphysis. I'm going to label it PE for proximal epiphysis. And this is our DE, distal epiphysis. So we have our proximal epiphysis and our distal epiphysis. Well, in between the epiphyses, I'm going to use a different color, in between the epiphyses and the diaphysis is a layer of cartilage. This layer of cartilage is called epiphyseal cartilage. Oh, let's see how long it takes me to write the word epiphyseal. Epiphyseal cartilage. I'm just going to write cart for cartilage. So there's our epiphyseal cartilage. And that's, of course, on both ends here. Well, that cartilage will begin to grow the same way that endochondral ossification grows. On either side of that cartilage, you're going to get osteocytes forming, in which case the bone is going to lengthen. It's causing the diaphysis to lengthen. So over time, this diaphysis is going to get longer because these epiphyseal plates made of epiphyseal cartilage will grow. When your growth stops, when you end puberty and you're now an adult and you're no longer growing in height, these epiphyseal plates, which are made of epiphyseal cartilage, are going to seal off. And they seal off and they're no longer able to grow. That's sometimes called your growth plate, where the growth will occur on the long bones. And once growth is ceasing, once you're entering adulthood and you're no longer growing in height, those epiphyseal cartilage will ossify themselves and become solid bone. So let's talk about this. The new chondrocytes form on the epiphyseal plate, as I was describing, and that cartilage on the diaphyseal side is going to be replaced by bone. So in other words, that diaphysis is going to lengthen. The epiphyseal plate is going to thicken, but the bone lengthens as well. That cartilage growth is going to stop in adulthood, and the epiphyseal plate is going to be replaced by bone, as I mentioned, and it eventually becomes what we call the epiphyseal line, which you can still see in x-rays. If you're an adult and you go to get, say, an x-ray of your tibia, your shin bone, you will still see the growth line there, that epiphyseal line. Bones can also grow in thickness, not just in length. So as it's growing in length, it's also going to be growing in thickness. And that's because osteoblasts are going to differentiate into osteocytes as the different lamellae are formed. The cells within the perichondrium differentiate into osteoblasts, and osteoblasts are going to calcify the matrix, so on and so forth. Osteoclast is going to break down the inner surface of that medullary cavity. So the medullary cavity is going to become thicker and thicker as well, or more open and more open as well. So as the bone grows in thickness, osteoclasts on the inner side of the medullary cavity, they're going to cause that medullary cavity to increase in diameter as well, to allow for increased storage of lipids or blood or whatever needs to be stored there. This is an animation of bone elongation and bone widening. Let's talk about bone remodeling. Osteoclasts and osteoblasts are going to help to balance each other out. They regulate bone formation and bone destruction. During childhood, osteoblasts are going to predominate. Osteoblasts are the bone builders, so those are the ones that are going to be working overtime, so to speak. During aging, there's more osteoclast activity, less bone formation, more bone loss as we age. This is why it's important to monitor your diet as you get older, because those osteoblasts are going to cease in functioning, and osteoclast activity is going to be activated much quicker if you have a nutritional deficiency. Remodeling is going to occur at different rates for different parts of the body to help maintain homeostasis. So different bones are going to be more sensitive to thinning and remodeling. For instance, your skull bones are not going to remodel as quickly as, say, your hip bones or your femur, for example. This animation goes through bone remodeling. Some factors that determine bone remodeling are hormones. The parathyroid hormone is a hormone that's going to stimulate bone building. It's going to stimulate the osteoblast. Calcitonin is going to do the opposite. It's going to stimulate osteoclast activity. Growth hormone, like insulin-like growth factors, are going to stimulate both cartilage and bone growth. And the sex hormones, estrogen and testosterone, are going to determine the sex-related differences in the skeletal growth. In other words, wider hips versus broader shoulders, etc. There are specific minerals like calcium, magnesium, and phosphate that are also going to play a role in bone remodeling, as well as some vitamins A, C, and D. Activity level, like weight-bearing exercise, is going to force your bones to grow. Someone that lives a more sedentary lifestyle is going to have thinner, weaker bones because their bones aren't being stressed, and that bone stress is what causes the bones to grow. So if you sit on the couch all day and just watch TV, your bones are going to be much weaker than someone who, say, is a runner or even a walker, because that constant stress that you're putting on your bones is going to tell them that they need to grow and they need to be able to support the stress that you're putting on them. Diet is also going to play a role, whether or not you're bringing these minerals into your body or not. If you're not bringing in the calcium, the magnesium, the vitamins, your body's not going to be able to store them in the bones, and therefore it's going to have to take those vitamins away from your bones to give to other areas of the body. When it comes down to it, your body would rather have deteriorating bones, say, than a deteriorating heart or a deteriorating brain. So your body's going to take minerals from these non-essential, for lack of a better term, body parts, like our bones, and give it to the essential parts, like our lungs, our heart, and our brain. This animation here goes through the regulation of bone growth. Let's talk about calcium homeostasis. I mentioned before how important calcium is, not just in our bones, but for all areas of our body, and we'll see a little bit of calcium pretty much from here on in every chapter. Over 90% of the calcium that is in our body is found within the bone matrix. The parathyroid gland is going to help detect low blood calcium levels, and then it's going to secrete the parathyroid hormone. Parathyroid hormone is going to stimulate the osteoclast to release calcium into the bloodstream. Kidneys are going to play a role in this too, and it's going to prevent any calcium that you had in your blood from being excreted in the urine. So in other words, it's going to prevent the excretion of calcium. Your intestines are going to bump up the absorption of calcium from food. So just because you bring something into your body doesn't mean it's getting into your blood. In some cases, different hormones, like parathyroid hormone, are going to influence exactly which types of nutrients your intestines are absorbing. If parathyroid hormone is present, your intestines are going to respond by absorbing extra calcium from the food that you're eating. Those calcium levels are then going to be increased because the parathyroid hormone has been secreted and restored so that you can maintain your homeostasis. Here's a little diagram for you to check out. So we have some type of stimulus causing decreasing blood calcium levels. Maybe you didn't drink your milk this morning, or maybe you've been exercising really hard and you haven't been watching your diet. So your blood calcium levels are low. Your parathyroid gland is going to detect that, and it's going to release parathyroid hormone. Parathyroid hormone is going to travel to various effectors, such as the osteoclasts. Osteoclasts are going to start breaking down our bones. It's also going to communicate to our kidneys and our intestines and say, hey, pull as much calcium from the food as possible. Don't get rid of any calcium in the urine. We need all the calcium in our blood we can get. So therefore, you'll see a response in the form of increased blood calcium levels, and then you get back to homeostasis. In the opposite, calcitonin is going to be secreted. So the thyroid gland secretes calcitonin. Calcitonin is going to be secreted when blood calcium levels are too high. So when blood calcium levels are too high, your osteoblasts are going to begin pulling calcium from the blood and using it to build bone matrix. It's also going to communicate to the kidneys and say, hey, we have so much extra calcium in our blood, go ahead and pee some of it out. Calcium levels are therefore going to be lowered and restored back to normal. Let's stop here for part 1.